So hello everyone. This is the fifth lecture of the mathematics and statistics of infectious disease outbreaks. I apologize for being a bit late recording this session, but I'm simply pressed with time at the moment. So I will record one part now and a part a bit later on. There are two topics to talk about today. It's continuing from what Tom talked about, is effective reproduction number estimation. We will consider this from a theoretical viewpoint in the first part, and then we will switch to a more applied view, and we will try to do some effective reproduction number estimates for Sweden based on the data from the Swedish Folkhälsomyndigheten. And just for comparison, we will also look at the production number estimation for Germany. So to continue is that Tom talked about in the previous lecture, we introduced the so-called basic reproduction number, also called R0, which was defined in the following matter, that we had three quantities which were important. So the first was the transmission or the contact rate. So this was the rate at which infectious individuals had contact with susceptible individuals. And we had the duration. Sorry, this is not the mean duration. 1 over gamma is the mean duration. So gamma is the rate at which you switch from the compartment of being infectious to being recovered. So the mean of this is 1 over gamma. And then we multiply by the either the total population size or how large the number of susceptibles was in the beginning. So you can multiply either by n or S0, it doesn't matter that much. So R0 was defined as to be the mean number of direct offspring that one infectious case generates in, and this is important and it's often forgotten, in a completely susceptible population without any intervention measures. So as Tom mentioned, of course, there are societal impacts on this, so it depends very much on how individuals have contact in the population which you consider, which could be very locally different depending on how dense the population is and so on. So one thing you and Tom discussed and you noticed is that once the epidemic unfolds, of course, susceptibles become less and less. So it's harder and harder for an infectious to make contact with a susceptible. And of course, this also has an impact on how many secondary cases this primary case can generate. So what happens if this completely susceptible population is not true anymore and we have a change in the number of susceptibles? So how does this affect the number of secondary offspring that you can make? And also, of course, depending on the disease, and for example, for COVID-19, this is very relevant, is that you either individuals themselves perform behavioral changes because they don't want to die. So of course, they try to change their behavior in order to avoid this. And of course, also the society itself, for example, by governmental interventions, tries to make it easier for the persons to perform these behavioral changes, or at least to guide them in the direction which is, from a public health perspective, good to try to minimize the impact of the disease. Of course, it's always hard to talk about. This is why I'm trying to find the political correct terms. A governmental intervention can also be a very unpopular thing, and so it's always a balancing between what are the rights of the individuals and what is it that a society can wants to accept in order to, for example, protect a particular vulnerable population. You have to rely on solidarity of those who may not be as much hit by the disease, but which can carry on the disease. So this is very important compared to, for example, if you talk about interventions against smoking, is that maybe smoking is even also a problematic example, because it's not just your own health that you affect by your actions, but also the health of others. So this is why it's important also to think about infectious diseases as something which is not sort of just your problem, because if you have a problem, it also becomes your neighbors or your contact person's problems. So this is why it's important to both assess what can the system do to sort of guide individuals into the favorable direction, but what is most important is what are the behavioral changes actually done by the individuals in the population. And these interventions or behavioral changes aim at reducing, for example, your infectious contact rate. Social distancing is one example, or that you do good contact tracing, so you try to reduce the number of contacts, the duration of how long people are being infectious, or you even try to decrease the amount of susceptible in the population, for example, by introducing vaccination. Good. So in order to, but one thing which becomes clear is that these here are maybe this one are going to be time-changing quantity, and as the epidemic unfolds, this is even also a time-changing quantity. So you need to do something about this. All right. So for this, and Tom introduced this more or less on his last slide, is that we define the time-varying effective reproduction number, and we call this R of t, as a time-varying quantity, and it denotes the average number of secondary cases generated at calendar time t. So this was opposite to the basic reproduction number, which is a time constant quantity, and we call this disease specific and society specific. And here there's actually also a time dimension. So it's not that it could be in the same society, but after changes, for example, due to fewer susceptibles. So if we assume the beta and the gamma to be constant, then we can define the effective reproduction number in a model-based way by simply saying it's old, R naught, and then multiplied by the proportion of susceptibles left in the population. So this is just one way to take care of the different number of susceptibles which evolve over the epidemic. But you can, of course, also, if you have more interventions aimed at beta and gamma, you can say, well, you could say you have additional interventions, and these will be covered here, and I will call these CFTs. It reduces the reproduction number, this one here, or the basic reproduction number, by a certain factor, 1 minus CFT. So the larger of CFT is, and CT will be between 0 and 1, the smaller is the effective reproduction number. So for example, one easy thing could be here that you say, well, we have vaccination here, so we reduce the proportion of susceptibles by 50% because we vaccinated 50% of the population, and it's a perfect vaccine. And in this case, then, of course, the proportion of susceptible is suddenly decreased that way. So this would be one intervention possible. But you could also imagine other things like that you try to do social distancing if you, for example, don't have a vaccine. So this equation here, already Tom had on his last slide, and I mean, fun fact is that actually this is also something, if you know this equation, you can start to represent this here on TV. So that is something which I saw Tom did, even on mainstream TV. So somebody commented that this is a typical spring TV program in Sweden in 2020, and that's when you know that you have an unusual situation when you in the national news are allowed to present such equations. So now you at least have some background where this equation is coming from, and this is what we will look at in more detail now. So how can we motivate the effective reproduction number? Now I'll try to give a bit of a sketch of how this looks, and if you want to have a bit more detail, you can look at the first couple of pages in the paper by Christoph Fraser from 2007, who introduces this. But it's, if you are really from a mathematical rigorous point of view, even this paper is not fully sufficient, and you need to dive deeper into differential equation, partial differential equation, and possibly even stochastic processes, but this is beyond the scope of this course. So let me just introduce an important component here, and this is called the transmissibility function, or beta t gamma. So it has two dimensions. It has a calendar time dimension, which we call t, and then it has a time since infection dimension, which is called tau. And this we use to characterize the development of the disease. So apologies for that. So let's maybe try to look at how this can look over time. And for this, I'm just going to make a small technical experiment. I will try new share. I will try to share the whiteboard, which should be here. All right, so let's see if this works. So we had, doesn't work. Here's the whiteboard. Okay. Right, so we said we had a function. Okay, new toy, new problem. So this is the function we were looking at. And this is something we want to make statements about. So let's say, let's ignore t for a while and just look at time since infection. So we have here time since infection. And here we have, so how infectious, what is the rate of contact? So we could say one component here could be virus shedding or how infectious you are. So for example, we could say this would be time 0, time since infection. This is where you got infected. And then it takes a certain amount of time before you are able to infect others. So let's say we really have a step function. And this here is your duration of infectiousness. And so this would be the length of this. And the height here would be sort of like how infectious you are. If you're very infectious, it's very high. If you're not as infectious, it might be more something like this, so a smaller value. So this would be very on-off type of infectiousness, but of course, really in real life, probably it's not going to look like this. It's probably going to be more like something like this. Again, here we have time since infection. And we probably have something like this. And maybe it will deteriorate over time. This is very interesting. This would be this is a single mode infectivity function, but you can actually have some which have double peaks. Like you have something which is initially high, then it turns out, and then you get something where you are more infectious like this. For example, HIV is something in that direction, right? So just to say, nature has all kinds of creativity for this. And of course, this is important to take into consideration. For example, one thing which is interesting is that, for example, for COVID-19, you would have here would be typically where you have your day of symptom onset. So it will be likely that you're most infectious just 1 or 2 days before your symptom onset. But of course, that makes it very hard to control such a disease, because the bulk of the infectivity is how many you can infect or how infectious you are is actually before you can actually, you as a person know it. And even if you want to do like contact tracing and so on, that's also before this is actually visible. So this is something which makes it a bit of a challenge to try to control this. And what you saw is that this function here is not just a function of a one dimension, which I've shown so far. Actually, it's a function of 2 dimension, right? So what we really have is that we need to draw this like we have here our calendar time. Let's call that the t, and here we had the TSI, time since infection. So we would say here that could be, for example, let's say we have here start of 2020. And here is the first Swedish case with COVID-19, just as an example. And then you would have what happens to this person would be a trajectory along the 45-degree line here, because with each day, day later, so 1 day later, he will also have an infection extra day of 1 day, right? So this would be, for example, day he got infected, and this would be the next day, right? And along this line here, in the third dimension, so this would here be the third dimension, the beta t tau, you would have that something is happening. And if you have the step profile, this could, for example, be, again, that we have a few days later, or there will be an infectivity, and it will stop again at some point. So this is, you can imagine this as a slice. And if somebody, for example, a couple of days later gets infected, he would have the same infectivity function always like this, right? So you can see this as a 3D slice. But the good thing is now we can also have public health interventions show here. So if you say you have some kind of public health interventions at this point, so people are not able to be as infectious as long time as before, because you're very efficient at trying to identify them. So you would have that. Let's see if we can get that. This would be the ordinary length, like there, but we are able to deduce this, so it would be shorter, right? So this is one way to try to mimic such a public health intervention. This is why there is this T component here, that this can actually also depend on time, calendar time. Okay, so this is the transmissibility function, or sometimes it's just also called the infectiousness of an infected individual, and this is what we will try to look at a bit more in detail. So I have to go back to the original sharing. Let's see if that works. That would be here. And the dependence on, as we saw on tau, could be due to time dependence, because there's viral shedding or changes in contact behavior after infections, because people stay at home, or maybe some of them are even so sick they cannot even leave anymore. So you also have a change in contact rate. So you can reflect all kinds of things in here. And important is that at the end, it's possible to describe a so-called renewal equation for all of this, is that you can say something about how the number of infectious at a given time point will evolve as a function of the old currently infectious and how transmissible they are. So you simply say, okay, the number of infectious at time t is simply the integral over all of this, and you say, well, it depends on how, if you go back for the time itself, it's not that relevant, but as further back you go, you will say, okay, those who are infectious, who turned infectious at time t-1 as an example, so if this is 1, then it is their infectivity component at time t, but with an infectious age of 1. So, I mean, this one here, this is actually quite complicated to show this. It has to do with stochastic processes, so we will not go into detail. I will just try to talk a bit about this here in a bit reduced setting, just maybe to try to illustrate that. So let's go back to the whiteboard. And this is something which is related to how the basic reproduction number was actually derived. It's related to demography. So this is actually not a concept which was introduced for infectious diseases, but for the growth of populations. And it was the head of the statistical office here in Berlin, Richard Böck, which in 1886 made a contribution called the total propagation of the population. And what he was interested in is to look at how the population is evolving, and for this he only looked at females and how they produce offspring. So this is a very typical way of how you study populations in the dynamics of population and demography. You simply just consider the female. So please allow me to sort of follow that view, because it's not a very reflected view, because it's only saying only the females are of interest, but for this purpose of what we are studying here, of course, this is from a mathematical point of view of interest. So what he said is, well, the number of births to a mother, and he said, I'm interested in birth of a mother at a particular age, right? So mothers, they have an age, and there's a certain period where there will be fertility, and where they will give birth to children. And what he looked at is a quantity, and let's see if we can get this here. Let's see. Not sure why this is not happening. It should be here. Sharing to front. Yeah, okay. Let's see. Hopefully here. So he looked at a quantity which I will simply call for this purpose here BTA. It's a bit different notation, but you can get that this is the T and the tau of the other one, and this is the number of births that a mother of age A has at time t. And he said this quantity actually is going to be equal to, well, those how many births will there be at time t by mothers of age A? Well, that depends, of course, how many mothers there would be at born. So they are now at age A. So of course this is related to how many mothers were born at time t minus A, because that's those who are either who we are interested in calculating the offspring for. And then he said, well, times the number of the expected number of offspring per year for mothers of age A, right? So this is the relationship that he considered. And then what he did is, okay, well, if you're summing that over all ages, it means that you say, well, we have to compute here overall ages. Summing means here we'll take the integral, because we're working with continuous age. So it's from A0 to infinity. And then it's BTA dA. And the same here on this side. So this is A equal to 0, infinity. And then we have here our BT minus A NA dA. And this quantity here, we will simply call what we have up there. That's the number of birth given at time t, disregarding the ages, so summing over all ages or the marginalized age part, right? So this is the equation that he did. This is simply a very heuristic way of showing what he did. This is related to demography, is also something which is called the Lot. It goes in the direction of something which is done by Lotka. But for our purposes, this is simply the I of t, which we were looking at. And here we are considering this expected number of offspring component, right? So as you saw from this beta TA, we want the component which has to do with one thing which controls the dynamics of this here is how much is the expected number of offspring. And this is, of course, what is related to the reproduction number, and here the effective reproduction number. So this is what we will look at in more detail. So let's change back to the slides, which we have here. So what we did is here try to motivate the quantity we just had here a bit heuristically. But now we have this equation here in the paper by Christopher Fraser. He introduces two concepts. What could be a possible reproduction number? So first is the so-called case reproduction number, which is more or less what I explained initially here with the offspring. is that we will look at our transmissibility function, and then we will simply say, okay, given a particular time t, what will happen in the future for this individual? How many offspring will they produce? Well, this is simply going to be the integral over infection age. So this will be as infection age evolves, but also calendar time, of course, also involved. So this will be simply be the integral here, while both tau moves, and as a consequence also t moves. So this will simply be, as you saw in my initial slide in this 2D diagram, it will be an integral along this diagonal line for this individual. This will be the case reproduction number. It looks into the future. Then he also defined, and this is what was new in that paper also, a quantity which was called the instantaneous reproduction number, which doesn't do this additional updating into also updating the time, but it simply updates the time since infection integral, right? So this is a slice which only goes like this here in this 2D diagram, which sometimes is also called the Lexis diagram. And this is a bit of a different interpretation. It's the average number of individuals and infected at time t is expected to infect, and this is the important thing here, which is different, should conditions remain unchanged, right? So calendar time is not updated, calendar time is staying fixed, so possible intervention in the future don't matter. We simply investigate what happens at t and then update that. And then he does a factorization of this quantity of this transmissibility component. Says, well, if it can be factorized as a product of something which is related to t and something which is related to tau, and then he says, since it's a product, it's okay to normalize one of them, so he can do it in every way you want. So he says, okay, I'm going to take index 1 and 2 is missing here. I should have added these. So it's, hang on, can I get that? Is that possible to do? Annotate, right? Draw like this. So here it, of course, should have been 1 and 2 here. I forgot that. Then he can show that this transmissibility function is simply the quantity he introduced as the reproduction number, and then something here which is the distribution of new infections as a function of time since infection. So this is what we will call the generation time. So given that there will be an infection, where will it be distributed in time since infection, right? This is what this quantity here relates, and this is what we'll call it's a continuous version of the generation time distribution. And then if he takes this result here, and inserts this into the equation we just had, and now just need to move on. Okay, yeah, and now I can move on. Then he gets that he has an equation for the instantaneous reproduction number, which is simply like this. So this is simply derived from the part before. And it says it's a fraction where you consider the number of currently infectious versus let's say that the infection pressure of the past. So this would be the part where you say, okay, I'm going to look back in time and see how much each of these individuals which are infectious at time t minus t, how many secondary cases they will sort of like how much it will be produced by them, and then you look at the ratio between these two. This is the so-called instantaneous reproduction number. And then you can also show that the case reproduction number is simply a weighted average over the instantaneous reproduction number. So what is the new quantity here, and this is the one we will look at, is the instantaneous reproduction number, which is defined in the following way. But of course, this is defined in continuous time, and typically you don't have I of t as a continuous function in time. What you have is aggregations over intervals. For example, how many new cases do you have per day? So you don't have the continuous time. You have, for example, how much is available over time. So we will say we only have this available for discrete time intervals. So for example, we could say, one would imagine that here we have our time and here we have I of t. And then let's say this is a function which goes like this, and here would be ti, and here would be ti I plus 1. So we don't have the development of this function, but what we know is, for example, how many cases are generated in this interval, and we will get sort of the area over this interval. That's what we will get. How many new cases were registered in that interval, and that would be the data which we would have, and which are, for example, collected by the Folkhälsomyndigheten. And what you can then do is simply take a discretized version of this one here, and then you say simply we don't have them in continuous time, we have it at particular time intervals. So that will be II would be the one associated with interval ti, and then you simply, instead of the integral, then you have to do the sum like this. And now these Vj's are simply the probability mass function of the generation time. So that is the discretized version of what we had here before in time since infection, right? Okay, so that will be a discretized version of this, and you can further say, okay, well, that's going to be our estimate. We have data for this, and we can compute this, but simply often what you want to do is you want to also cast this into a distributional framework and say instead that can we say something with distribution, because this will then make the R of ti a parameter in a statistical model, and then we can use the entire tool set which you know from which you know either already know, or that which, if you're interested in statistics, something which you will learn about more as you progress through your studies. We can simply do a distributional assumption and say, okay, let's say that the number of cases for time interval ti will be ii, given the past, which we already know, so we don't have to, we can condition on that because that's something we have seen, will be a Poisson distributed random variable, and with this structure here as before. And then you, if you have done a bit of statistics, you know already that RTI, the maximum likelihood, or the method of moments estimate for this, will simply be this quantity here divided by all of this, and which is exactly what we would have here. But in addition, you would also have the opportunity to construct confidence intervals or credibility regions for RT of I. So this is a very powerful, as soon as you, of course, are also going to believe in this distribution. So this means, for example, that the expectation is going to be this. The variance of what you observe will also be likely be equal to this. So this is also one thing where you already say, well, maybe fluctuations are actually a bit bigger than that, and then maybe the Poisson distribution here is not the right assumption, and so on and so on. But this is, for example, what is often used in practice because it's a count data distribution, and the II are, of course, counts because it's the number of new infections. What you can do furthermore, and maybe I'll remove the annotation part, is that you can not compute the TI for one time point, because then you will, as you can see here, you won't have a lot of, you will have exactly one observation for all of this, and this can be a bit jumpy because there's fluctuations in all of this. So the authors of a very popular method which uses the instantaneous reproduction number, they say don't use that for one time point only, compute instead an instantaneous reproduction number over an interval of tau days. So it will, for example, be typically you will take a week in order to get day of the week effects out of all of this. So what you say is, I'm not just going to take here tau equal to 1. That's the one we simply seen, because that would be II in this case. But you, in the numerator, you take the most actual value and tau minus 1 previous values for all of this, and then you will divide by always this contribution here, always again shifted by 1 as you go back in time, right? So this will be this quantity here. So this is well, maybe it's easier to do a bit of a graphic. I've put an exercise once you assume a fixed generation time of 4 days. I put a small in an exercise so you can try to see how this actually looks. And but please note, this is a way that you say in the numerator I have something, and then in the denominator I go back in time several times. So this is a bit, it's not exactly the same, but it's very similar to simply saying I'm just going to average my instantaneous reproduction number that I get for the past tau days. But this is a bit of a different quantity than what is suggested here. And one reason for this is then you can still operate here in the Poisson framework, because you simply again have counts here, you have a weighted sum of counts here, which is only in the past. So this allows you to also again have a distributional assumption and form confidence intervals and credibility regions and so on. Right, so in the practical part in implementation results, we will look in more detail how this looks for when you actually use data. But so far, it's just important to remember you can calculate the instantaneous reproduction number given discretized or aggregated data in, for example, daily or weekly form. But you need to be careful because there's a lot of fluctuation in this. You may want to smooth or average over an interval in time. And if you have daily data, I strongly suggest that you at least take a week, because there will usually be weekly effects seen in what you are in your data. Okay, so and this is just sort of like, so far we talked a lot about the average or the mean number of offspring one infectious case generates, and I would just want to sort of at this point highlight, and we're not going to go a lot in detail for this, is something which again has come up with COVID-19, and especially because it was very relevant for SARS, so the SARS-CoV-1 virus, so the 2002 to 2004 outbreak, is that it's not just the mean of the offspring distribution which is important, it's also the variability in the offspring distribution. And this is something which is not captured by the R0 per se, because this only looks at the mean. And the reason, and I'm not sure Tom will talk about this, but you will see that once you look at interventions is, of course, and we will simply sketch it, is that this also makes it the probability of extinction, that you don't have a large outbreaks. This makes this probability a bit bigger if you have a very large variability in the offspring distribution, and maybe it makes the disease easier to control. So this is something which, at least in Germany, was a bit of an issue, and maybe we can talk a bit more about that in the live session later today. But what is important to know is that, okay, let's look at this variability, and for this is good to know as a background the SIR continuous time Markov chain model, which we also simply call the stochastic SIR model, or the general epidemic model. The constant infectious contact rate and a constant recovery rate, this leads to the offspring distribution, so that's the number of secondary cases which one primary case generates. This will be a geometric distribution. If you don't know what a geometric distribution is, please look it up, for example, on Wikipedia, but you probably have heard about this before. Anyway, so there's an exercise to play with this. I hope this is not too difficult. For some of you which are in first and second semester and have never done any statistics, this might be a bit difficult. So I've tried here to give a hint, which is simply insert probability mass functions and do an integral. But I give me some feedback if this is too difficult for you. I think we, as I saw from the survey, we have a very mixed audience. Many of you have many years of study, and some of you don't have a lot of study. So we'll try to sort of find a good way. So maybe have a look at this. Okay, so this is a famous paper by Lloyd Smith from 2005, which analyzed the SARS-CoV-1 outbreak. And what was interesting there, that the entire epidemic was driven by a small number of very specific events where one primary case infected a huge number of secondary cases. So there was one incidence, for example, on an airplane where somebody infected, I think it was more than 20 cases. One patient at a hotel, and because it was aerosol driven by the what do you call that? The air condition, it spread through some of the rooms. So he also managed to infect a huge number of individuals were infected because of this one individual. So he had really a few incidents with a very large number of secondary cases. And on the other hand, a lot of individuals which got SARS-CoV-1 didn't really infect any others. So it wasn't really, the mean was not a very representative summary statistics of the offspring distribution. And it had, and what is important here is of the variance of it was much larger than implied by the geometric distribution. So instead, in this paper here, which is a Nature paper, it's in the reference. I think it's actually possible to read if you're interested in stuff like that. They suggest the so-called the negative binomial distribution with a certain mean equal to our effective reproduction number and an over dispersion parameter k, so it has more flexibility. So there's you can parameterize this, so this is equal to the geometric distribution. If k goes to infinity, this is simply the Poisson distribution, but this is, you can also again look it up on Wikipedia, what is the negative binomial distribution. You get some insights there, but they allow for a more flexible distribution. And what is important for this is since this epidemic is driven by a small number of large so-called super spread events, so super spreading, if you can knock out the opportunity for these super spreading events to happen, then you have a very good chance that you actually are able to contain such an outbreak, because sort of this is what drives the epidemic, is these small, they don't occur often, but the small number of large events. So what could be an explanation for that? Well, you have to be sort of like, you are only infectious in a very narrow time window. You have to have the opportunity to infect a large number of persons. So you have to, this has to be given. For example, you go to a concert or to a choir and you sing loud and you are many people in a crowded room. Would be some events, or for example, you are the air condition has a flow, so your air is spread to many people which are susceptible. So you have to have a lot of people in closed space, for example. That's the one opportunity for this to happen, and then you have these super spreading events. Just to sort of illustrate this, so here I showed with red would be the geometric distribution, which has a mean of 2.5. So this would look like this. So you see the majority of individuals has, of course, it doesn't infect anybody. And then, of course, you have a certain probability for these bigger numbers to happen. But if you compare to the negative binomial with the same mean 2.5, but with an over dispersion parameter of 0.45, then you see, well, it stretches the distribution more out. So you have a larger number of people who don't infect anyone, but you also have a larger number of people which, and I caught it here at 20, but the probability is sort of like, it's not, you can see it, it's not that clear, but you have a very long tail of this distribution. So you can infect quite a large number, but in order to still have the same mean, of course, that means also this one here is going to be larger. And the idea now behind the control is these number of secondary cases, this is what happens in the household, this is what happens in regular work context. This is the thing which is going to be hard to contain, because you really have to make drastic measures to try to reduce this. But these super spreading events, this could be mass gatherings, this could be, for example, very specific workplaces which are very crowded, like meat packaging facilities, or where the housing conditions are difficult. This is something which you, at least still with a lot of effort, but still economically somewhat cheaper than trying to sort of like ban everybody from having contact with more than one person at a time. You can maybe, if you know this offspring distribution, then you maybe have a bit of a better chance to try to control the outbreak. So this is the idea behind this, is to try to say, well, the mean is not necessarily the only quantity which is relevant for the offspring distribution, and that was the effective reproduction number, maybe also variability is. And I think this is for you good to know. Right. So this brings us to the end of this first part. I will do the second part later in the afternoon, but I'm sorry, it will also take a while before I get it online. And so I hope you can at least enjoy this part of the talk, and I will see you later for the second part with the data part, and also for the for our live session. So I'm going to stop sharing and also stop the recording. See you then.